Okay, we have a little bit more to learn about motion graphs. We're going to learn about two more kinds of motion diagram or motion graphs in this video, velocity versus time and acceleration versus time. But before we start all that, I'm going to do the position versus time graph and show you how they all relate to one another. So this position versus time graph, I'm going to do the position dots in blue, and then I'll do the velocity and acceleration graphs in other colors, and I'll just overlay them all, and it'll be super great. So this object, I'm not even going to explain what it is. I'm just going to draw the graph of what it's doing. And we'll learn what kind of objects do this over the next few weeks. So this is an object that I hope you can kind of see what it's doing already as far as its graph. We started at 0, then we went to 1, 4, 9, and 16. It's not a coincidence if you're noticing the pattern there. So this is its position. After 1 second, it was at 1 meter. After 2 seconds, it was at 4. After 3 seconds, it was at 9 meters. After 4 seconds, it was at 16 meters. So this object, it's traveling a little bit further each second that passes. If we drew the velocity graph for this fella, the velocity graph would look like so. There's a good reason for why the graph looks like this. And I'm going to kind of help set that up by starting to show you some of the important features. So that red line, by the way, was the velocity in meters per second. So let's notice some stuff about this red line. I'm going to calculate this area right here under the curve. This is a triangle, and a triangle can always be calculated by doing 1/2 base times height. So that's going to be 1/2. The base of this triangle is 1 second, and the height of it is 2 meters per second. It's meters per second again because that's the units of this axis. And if you calculate that out, that's 1/2 times 1 times 2. We're going to get 1. But then I have seconds here on the top of this number, but on the bottom of this number. So if you remember like math or maybe in chemistry, one number on the top, one number on the bottom will end up canceling. And so we end up with just meters left over. So this is 1 meter. If I move forward and I do not the area from 0 to 1, but the area under the red line from 0 to 2, so this whole area there, that's going to be 1/2 base times height again, except now my base is 2, and my height on the red line is all the way up to 4. 1/2 times 2, those cancel, and I get 4 meters. And notice that the blue dot is at 4 meters. Here, when we figured out the air end of the line, the blue dot was at 1 meter. Here, it's at 4 meters. Probably, if I calculate my next one, 1/2 base times height all the way from 0 to 3, I would get 1/2 times 3 times 6, and I'm going to get 9 out of there. Oops, I shouldn't write an exclamation point. That makes it look like it's factorial. So it's 9 meters. So this tells us an important fact. It tells us that on a velocity versus time graph, velocity versus time, oops, it doesn't like that I just clicked on my own picture. On a velocity versus time graph, the area under the curve is the displacement. And that's always true. But we can also notice another interesting feature if we do a little bit more observing the numbers. So let's, well, we actually already knew that the slope of this graph in blue, this one, the slope was equal to the velocity because the slope of it would end up being meters per second. So slope of the position graph gives us velocity data. Area under the curve of a velocity graph tells us displacement information. So we can figure out some of the information from each graph by looking at the other. The next thing that we can figure out with the velocity graph is we can do the slope of this graph. And the slope of this graph, it's still rise over run. The rise is meters per second, or its velocity. So it would be a change in velocity over the run, which is a change in time. And change in velocity over time is the acceleration. So that gave us the acceleration now. Let's actually use those numbers to figure out what the acceleration graph is going to look like. So right here, I went over 1 and up 2. So if I was calculating the slope, it looks like my slope is 2 along here. So I don't like how that turned out. You know what? It's probably where I need to change the pen like this. There we go. Okay. And then along this area, I went over 1 and I still only went up 2. I mean, I'm 4 high, but I went from 2 to 4. So once again, I only had a rise of 2. And going all the way across, this green line is our acceleration in meters per second. And you can see that we can figure out the acceleration from the velocity graph by using the slope. Last thing that we can do is we can figure out on an acceleration versus time graph, there's some information we can get here from the area. So let's calculate the areas here. Notice that my area under this line, it's 1 over and 2 up. That's an area of 2. And 2 is my velocity at that position. If I go a little bit further over, all the way over to there, now my area for this whole box is 4. And notice that my velocity is at 4. My area all the way over to 3 would be 6. That's 3 times 2, which is 6. And notice that my velocity is 6. Let's see. Right here, we can see that the velocity is 8. I wonder what my area under the curve is all the way over to there. And if we calculate it, look at that. It's 8. So the area on this graph is equal to the velocity. So final takeaway. This is the part that has to go in your notes. We want to make sure that we definitely remember it. If we have a position, a velocity, and an acceleration graph, or acceleration graphs, then using the slope from the position graph, oops, let's rewrite that. Using the slope from the position graph, we can figure out velocity information. Using the slope from the velocity graph, we can figure out acceleration information. Using the area under the curve on an acceleration graph, we can start figuring out what's happening with the velocity. And using the velocity graph, we can figure out information about the area. I just want to throw in 2 caveats. Here, this only gives us the average. Whatever 2 points we use for our slope, we'll only get the average acceleration or the average velocity between those 2 points. If I had a position versus time graph that looks like that, and I used those 2 points, I might not get a very accurate idea of what the velocity is because I'm missing this weird dip in the middle. But I would at least get an average velocity. I would get some kind of idea of what happened during that period. For this area down here, the area, it's not actually telling us, the acceleration doesn't tell us the velocity, or the area of the velocity graph doesn't tell us the position. What it tells us is the change. So by using the area, we can figure out how much the velocity is changing by on the acceleration graph. By using the velocity information, we can figure out how much the position changes, but we can't actually figure out the exact values without already knowing some information about it, where it was. So if we know where it started and we can figure out the change, then we know where it ends. Otherwise, we can just know it ended up 10 meters further down than it started. So you'll see some examples of that, but this is the big takeaway that I want you guys to have from this video. So thank you very much for for watching and have a great night or afternoon or whatever.